In this task, I'll use a digital elevation model to create several terrain-related datasets: slope, aspect, and hillshade. These elevation-derived datasets can be really important in site selection analyses and other terrain-based spatial analyses. Here I have QGIS Desktop open with a DEM loaded. This particular dataset covers the Sandia Mountains on the east side of Albuquerque, New Mexico. And this is what we would call a continuous dataset. In a continuous raster, the phenomena represented have no clear boundaries. Here the pixel values represent elevations above sea level, and the white areas would have the highest elevation and the dark areas the lowest elevation. I'll start out by investigating this layer. I'm going to open up the layer properties by double clicking on it, and I'll start out on the General tab. And you can see that the spatial reference for this dataset is UTM Zone 13 North, NAD 83. And UTM has its XY coordinate values in meters. Now I'm going to switch to the Metadata tab. Down at the bottom, you'll see the properties. If I scroll down a little bit, you'll see there's a listing for pixel size, and it lists it by 10 by -10. Since the UTM XY coordinate values are in meters, this means that each pixel represents a 10 by 10 meter area in the real world. Now I'll switch to the Style tab. And you can see that the min and max here goes from 1841 to 3094. However, the load min max values default is cumulative count cut, which is eliminating the bottom 2% and the top 2% of the values, and the accuracy is defaulting to estimated instead of actual. I'm going to switch this to min max and the accuracy to actual and click load, and you'll see the values change to the actual min and max, 1775 to 3255. The elevation or Z values of a DEM are typically either in feet or meters. The Sandia mountain range represented here reaches an altitude of 10,678 feet above sea level. Therefore, I can deduce that these elevation units are in meters. And before working with DEMs to produce derived products, it's important to understand what both the X, Y, and Z values are in. Here, all three of my units, X, Y, and Z, are all in meters. I'll finish this section just by clicking OK, and you'll see a slight shift in the styling of the data because now the stretch from black to white is covering the full range of values. Now I'm going to use the raster terrain analysis plugin to create the three elevation-related data sets. Since this is a plugin, I'm going to go to the Plugins menu, Manage and Install Plugins. And I'm on the Installed tab. This is a core QGIS plugin, so it should be installed. If not, you can always switch to the All tab and search for terrain, find it, and install it. Since mine's installed, I'm just going to click the box next to it to enable it and click Close. Now I'll demonstrate how to create a hillshade image, which will allow you to get a better feel for the terrain in this area. Hillshades are very useful for creating nice maps. From the menu bar, I'm going to choose Raster, and you'll see a new entry for terrain analysis, and I'm going to choose Hillshade. We only have one layer, so this DEM is going to be the elevation layer. I'm going to choose an output, so I'm going to navigate to the Lab 7 My Data folder, and I'll call this hillshade.img. Click Save. I'll choose ERDAS Imagine Images as the output format to match the output layer name I just provided. The Z factor is a conversion unit between the X, Y, and Z coordinate values of your data set. Since all my values are in meters, X, Y, and Z, I'll leave this at 1. If my elevation units were in feet, I would have to put a conversion factor from feet to meters in this spot. I'll take the defaults for azimuth and vertical angle and keep Add Result to Project checked, and click OK to run the tool. It calculates the hillshade and puts the layer on top of the table of contents, and now you can really get a nice visual of the terrain of the area. And just for reference, Albuquerque is on the west side here, and you can actually see the road that goes up to the ski area, and these are the actual ski runs on the mountain. So you get a lot of detail in this 10 meter by 10 meter digital elevation model. So this is a grayscale hillshade, and now I'm going to demonstrate how to create a color hillshade image by combining the elevation data and the hillshade data. First, I'm going to drag the hillshade below the DEM. And now I'm going to open up the layer properties for the DEM and go to the Style tab. I'm going to change the renderer type to single band pseudo color. I'm going to change the color ramp to one that's more terrain based, the brown to blue to green. And I'm going to change this to load min max values and the accuracy to actual. Now I'll click the classify button. And before I close my layer properties, I'm going to go to the transparency tab and make the global transparency 50%. I'm going to click OK. So now I've colored the DEM based on elevation with some terrain-related colors, and I've made it semi-transparent so I can see the hillshade through it, creating a color hillshade image. Next, I'll create a slope data set. I'm going to go back to the raster menu, to terrain analysis, slope. So in creating the slope, the elevation is going to be the input, so you have to make sure that you don't pick hillshade. You'll get an odd result. We want the elevation to feed into the slope tool. The output layer I'll just call slope. Click Save, and I'll make sure the output format matches my output layer type. My Z factor again can stay as 1, and I'll click OK. It calculates the slope. So the resulting raster shows the steepest areas in white and the flattest terrain in black. The tool determines the steepness of each pixel by comparing the elevation value of each individual pixel to that of the 8 surrounding pixels. This is what we call a moving window analysis. It does this from pixel to pixel to pixel to pixel until it's done it for the entire image. And the slope values are degrees of slope. Finally, I'll create an aspect data set. I'll go to the raster menu again, to terrain analysis, aspect. Again, I want the DEM to be my input. The output I'll just call aspect. I'll leave the output format and the Z factor as ERDAS Imagine and 1 respectively, and click OK. It's placed aspect below slope, so I'm going to drag this to the top of the table of contents. Okay, so here's my aspect data set. Aspect measures which cardinal direction the terrain in each pixel is facing. So, for example, north facing versus south facing. And the output values range from 0 to 360. 0 being a north facing pixel, 90 being east, 180 south, 270 west facing. In the next task, you'll learn some GRASS tools for reclassifying these raster datasets into meaningful categories.